and try exercise again. So there were several questions after the previous class, and let me just answer the questions as well. So this is from lecture 4, the definition of value function and Q-value function. As I said, value function, it says about how good is a state, and it is a function that takes state as an input. And the mathematical definition is expected cumulative reward from following the policy from state S. And Q function is also about predicting future state, but it additionally takes action into account. So how good is the state-action pair? So it's about how good the state about the value, and Q-value function is about the how good is the state-action pair. And the mathematical definition is almost the same. So Q-value state S and action A is expected cumulative reward from taking action A in state S and then following the policy. So there were exercise, and let's try this one again. So this one shows that, so our goal is getting value function, and the actions here are predefined. So these are action, all these are actions are predefined. So how can we get value from these predefined actions? So let's first start this one, this state, and reward is defined like this. This is reward function. And if entering state 0, entering 5, entering 6, otherwise, how about this one? So 1, 2, 3, 4, 6. So these are state. No, state is start with 0, 1, 2, 3, 4, 5, 6. These are state indices. And how about state S? It just revisits state 5, right? It's not entering state 5. So the reward is 0. So that is the reason why we have 0. Because in the previous slide, we have the definition of value function is just the expected cumulative reward, right? So, I mean, in state 5, we infinitely revisit state 5 so that we do not have any reward. So just keep adding 0 so that we have just a 0 value. So that is the reason why we have 0 value in here. This one as well, and here we have action, predefined action, right? And entering state 5 so that we have 3. And how about this one? Predefined action is entering state 4, right? Entering state 4, but according to predefined reward function, entering state 4 does not have reward. So we start with the 0 plus and then discounted reward. And then from the state 4, we have predefined action that entering state 5. So that 0.9 times 3, that becomes 2.7. This one is for this one. And here, let's start with this one. Here we have predefined action function is predefined action is just going left. And it's about entering state 0. So that -2, and then next one are just 0, right? Because once we enter state 0, then the predefined action is just revisit state 0, and it belongs to this condition. So that we have just 0. That gives us -2 as a value function. This one, the predefined action is entering state 1, which belongs to 0 reward, right? So start with 0, and then next one, discount, and then and predefined action function from state 1 is entering state 0, which is -2, so that we have -2, and then once we enter state 0, then remainings are just 0, so that we have -1.8, right? So this one shows that we try to get value function with predefined actions, where predefined actions are illustrated with the blue arrow, and these numbers are value function. You can just simply follow the definition of value function. And this one as well. So we start with 0, 0, 0 for these cases, and then for this one, the predefined action is entering to this state 6, right? So that it starts with the how about this one? 7 plus, and then once we enter state 6, then the reward is 0, so that 0. So that the value function is 7. And here, all the predefined actions are just going right? So that in this case, entering 1, 2, 3, 4, 5, 6. Entering state 4, 3, 2 belongs to this class, so that we just start with the 0 and then until we reach to state 4, right? And then state 4, it has value 7, so that we have 6.3. These ones are as well, just entering this state, it gives us 0 reward, but once we reach to this one, then we can get reward 7, so that 0.2 square and then 7, right? This one is also the same. This is easy, right? This is not difficult. And then we actually also learned about the stochastic environment. So far, we've only covered deterministic environment, so that an action deterministically determines next state. There is no probability. But stochastic environment, we have probability, like this kind of probability. So the probability from state S4 and the probability of next state from state 4 of being state 6 is 0.5, and from state 4, what is the probability of next state being state 5 is 0.5, right? So that what is the so star is an optimal optimal value function from state 4. And then we've learned this kind of one from lecture 4 as well. We can just rewrite this as a Bellman equation. Expected reward, where R is from SNA. R is from SNA, and other ones are just a discounted summation of future reward, assuming all these actions are optimal, right? That is a recursive formulation of the Q function, right? That is the basic definition of Q value function, and assuming optimal, Q function is optimal with the star notation, then we can rewrite this one into this kind of Bellman equation, recursive formation. So then, how about this one? V star S4. So let's revisit this one. You can memorize this one, right? So that expectation means we need to multiply probability, right? So that this one, we have probability of 0.5, 0.5, and then possible action of this one is just 3, so that we have reward 3, and then 0.5, 7 gives us 5, so that we have 5, right? And remaining things, so some student asked me about why we do not multiply probability for this state, right? We only multiply state for, multiply probability for this state, but we did not multiply probability for remaining state, right? This state, this states. So the problem was a little bit unclear, but unless there's a specific description, we assume remaining states are deterministic. So this one is stochastic, so there's a probability, right? The probability, so that it indicates state 5 is like some in stochastic environment, but the remaining state, we assume they are deterministic. That is a more clear description of this problem. Of course, we can assume all these are stochastic as well. Of course, we can assume all states are stochastic, but that makes problem much more difficult, which is too difficult for the first exercise. So I think this exercise, for remaining states, we assume all states are deterministic, other than this one. This state is only a stochastic state, and then remaining states are deterministic. And then another thing we assume is that we know, so we actually knows all the environment. That is actually called model-based RL. Model-based RL. That means we are like a God. We are like a God, and we know all the environment, and we know this kind of, once we go left, then we will get very small reward, -2, which is much smaller than going right? So we know all this kind of situation in environment, that is called model-based one. We know all the kind of model, and then that is called model-based reinforcement learning. We will learn in next exercise, actually, it is model-free RL. We will cover in next slide. So anyway, this exercise assume model-based RL, and then another assumption is that all states other than state 4 are deterministic. These are some descriptions that needs to be added for this exercise. In this case, then, for this one, how about this one, state 3? State 3, according to this model, we know that once we go left, if we go left, then we will get this kind of too small reward, so that according to model-based RL, the model should go to right to make the value function optimal, and then to get value functions maximized, right? And deterministic, so there is no probability for other states. So that we have the value function, optimal value function for the state 3 is just once we go here, then we have definition here, right? R from SNA. So entering this state goes 0, right? According to the reward, 0 reward. And then discount factor 5. That gives us 4.5. All these are the same. Once we go left, then we know that we will get too small reward. But there is no reason that we need to go to left, according to model-based RL. We know all the things in the environment, so that to make value functions optimal, it needs to be maximized. And to this end, we need to go right to get the high reward, 7, instead of -2. And all the actions are deterministic, all the states and actions are deterministic other than S4, so that there is no probability. And then the problem becomes much simpler. Just we can multiply 0 plus 0.9 and 4.5. That gives us 4.005, and here is 0 plus 0.9 times 4.05. That gives us 3.64, right? We already calculated optimal value function for this one and then this one, right? It's like dynamic programming. According to this one, we already calculated this one. We already calculated optimal value functions for the next state, right? So that we can simply retrieve such kind of pre-calculated optimal value function and then put into the Bellman equation, right? So these are some assumptions that needs to be added for this exercise. Is it good? Any questions about this exercise? Okay. And value function, as I said, is that like it tries to evaluate quality of a pair of state and action, total discount reward of taking an action A in state S, assuming all future actions are optimal, right? And then, so how to get optimal Q value function? So optimal Q value function is notated by Q star, and there were 2 algorithms that we learned in previous class. The first one is always take random action, right? So we first make a table, 2D table, S and A, and then we fill all Q value as a 0. We fill all numbers as initial values as a 0. And then we update this table until we reach to some predefined iteration. That is how we can get optimal Q value function. And the most brute force naive way algorithm is just taking random action. Always take random action. And then update the Q value with the randomly taken action. And from initial state S. Of course, this too naive and brute force way. It's too slow for convergence. And that is the algorithm 1. And the second algorithm was a epsilon greedy online learning of Q function. So only difference is this one. Only difference is this one. Instead of taking random action, instead of taking always random action, with some probability, which is hyperparameter of this algorithm, epsilon, with the probability of 1 minus epsilon, take a greedy action. Otherwise, with probability epsilon, take a random action. So the goal is to exploit what we've learned so far, right? So this one, greedy action. Greedy action means it tries to use some numbers in our optimized Q-value function, right? So all the numbers are initialized as 0 at the first of the algorithm, very beginning of the algorithm. But after some iteration, maybe, after some iteration, some numbers are filled with non-zero values, right? And then we can exploit such numbers instead of always taking random action, so that we can, that is called exploit. Exploit means use or utilize. So sometimes we take a greedy solution so that we try to exploit what we've learned so far. But always taking greedy solution will lead to local minima, because we need to explore the environment so that with some probability we take a random action, explore new action. So there's a hyperparameter called epsilon to make a balance between exploitation and exploration. Third one is new one. It is newly added in the updated lecture slide. It's not also very complicated. So the epsilon, so the name is epsilon grade online learning of Q function. So that means we also have epsilon. It's the same. We probability 1 minus epsilon take the greedy action. Otherwise, we probability epsilon take a random action. It's the same. But the difference is that we have additional learning rate here. It's new hyperparameter as well. We introduced learning rate, right? And the difference from algorithm 2 is that how we update Q-value function is different. This one is different. The only difference is this one. It's like a soft update for stability. So in previous algorithm 2, we just simply updated Q function with the R plus gamma with the maximal Q function. That is different definition of the optimal Q-value function and Bellman equation, right? So instead of, it could somehow overwrite, completely overwrite what we've learned so far. So it could make algorithm unstable and oscillating. So instead of completely overriding what we've learned so far, for every iteration, we make some kind of sort buffer so that it tries to keep what we've learned so far, but also it tries to learn what we've so far by adjusting learning rate alpha. So soft update stability prevents the Q table from oscillating by observing new experiences incrementally rather than overriding existing knowledge, right? So from equation, some mathematical formulation, we know that 1 minus alpha and alpha is like a linear interpolation between current value and update with deterministic transition, right? So it's like algorithm 2 is a special case where alpha is 1. Algorithm 2 is a special case where alpha is 1, right? So that we completely ignore current value and just always update with the new one. So that algorithm 2 is a special case of algorithm 3 where alpha is 1, right? So that we average in stochastic outcome. So naturally converge to expected value here over time by smoothing out random environmental noise without explicit probability calculations. So here we actually do not have probability, right? According to the definition of optimal Q-value function from this slide, we always have expectation, right? But the problem is that in many cases, we do not know probability in advance. Let's say we have some robots and let robots move around the current environment. We do not know probability of probability robots going from here to here, or here to there. We do not know any probability in advance, right? So we need lots of exploration to make the Q table converge to expectation by trying lots of iteration. That is the philosophy of this kind of learning rate. this kind of law of big numbers. So we try many times, so then it will converge to expectation without explicit knowledge of probability in advance. Right? Because we average current value and updated value many times, and then we converge to expectation. Then we can rewrite this one. We can, it's just the same, but then we can just rewrite previous one with this one. It's not a different algorithm, the same algorithm, but we can just use different mathematical formulation from the previous one. We can just, we have 1 minus alpha, right? So we let alpha here, and minus alpha is added to the right term so that we can put the minus QSA into this alpha term. So current value is the what we've learned so far, and this is a temporal difference, right? It's like we know gradient descent, right? It's like a gradient descent. From current value, we have learning rate, and then this is a delta, temporal difference, delta. It's like R plus gamma max Q S prime A prime is a new one that we've learned from, that we've explored. It's like a new Q value, and then this one is our current value, so that delta between current one and new one could be seen like a gradient, and then we multiply it with alpha so that it looks similar to gradient descent, right? We have learning rate. So that if we use high learning rate, we'd like to include this kind of delta much. If alpha is 0, then we ignore new one, just keep the Q value as the initial one. So alpha is hyperparameter. Is okay? And let's take example as well. So we covered this one, and then let's see how we can these numbers. So the problem of current previous slide was so assuming we have this kind of environment. This is assumption. Reward function is predefined like this one, and then which one correspond to optimal Q value function? That was the question, and the answer was this one, the bottom one. And firstly, we must calculate the optimal value function to make the calculation easy. And optimal value functions are shown in green numbers. So these ones, so the blue ones are, so here, let me clarify. Blue, Q star, green, V star, okay, and red, reward. So then from this reward function, we can compute the optimal value function V star, right? So this one, as there's no explicit description whether this environment is stochastic or deterministic, as I said. Unless we do not have explicit description, we assume environments are deterministic, so that there is no probability. And then let's compute the V star then from reward red ones reward. So from this one, how about the optimal value function for state 4? Of course, 7, right? We need to maximize the cumulative reward, right? So that is the reason why we have 7 V star. And how about this one? It's almost the same as the previous stochastic environment example without probability. We know all the things of the environment, right? We know all the things in environment, model-based reinforcement learning. And then if we go to left, and then we will get negative reward, which is not desirable. So we need to go right, so that the optimal action to make it value function optimal is going right. So that 6.3 is from entering to state 4. It gives us 0 reward, right? State 0 reward. And then we already computed optimal value function for the state 4, so that 6.3. This one as well, all the same. To make the value function maximize, optimal, we need to go right, so that entering right state gives us 0 reward, as you can see here, 0, 0. But we already calculated optimal value function for state 3, state 4, so that we can just retrieve such kind of pretty pre-computed optimal value function. It's like dynamic programming. So that this one, for example, 0.9 times 6.3, and this one 0.9 times 5.67. So that we computed value function, and then now our goal is getting optimal Q value function. How can we get Q value function? So this one is like we need to specify state and action, so that from state 4 going to state 6, it gives us reward 7, right? So these are optimal Q value function for this one. And then from state 3, how can we get this one? State 3, reward from going, so how can we get, this is the value function. This is value function. How can we get this number? This number, state 3 to state 4, it gives us 0 reward, right? 0 reward. And then we already computed and then we optimized Q value function 7, right? This one is higher than 3, right? So that we can multiply 7 with 0.9 so that we can get 6.3. And how about this one? This one also 5.67. From state 4 to state 3, it gives us 0 reward, right? So 0 plus, and then what is the optimal value function for optimal Q function for state 3? For state 3, we have multiple actions. We can go right, we can go left, but we know that once we go left, then we will get minimal reward, right? So that among possible actions, going left and going right, we need to choose this one. This is consistent with definition. This one. We need to pick a optimal action that can maximize Q value function. So that we need to pick action that can maximize reward, which is going right, so that we can multiply 0.9 times 6.3. That gives us 5.67, right? Many things are the same, just how about this one? Entering state 3 gives us 0, and then 0.9. And from state 3, what is the optimal one? Of course, going right, right? Going from state 3, there is 2 actions that we can take. Going right and going left. Going right gives us higher Q function, right? So that we need to choose 6.3. That gives us 5.67. Many things are the same. So is it okay? So it's almost the same as the previous value function example with stochastic environment, but the difference is that this environment is fully deterministic and also model-based RL. That is difference. Another one is that we take care about Q function, not value function. And this one, so far we studied how can we get Q function from model-based RL. Model-based RL means we know everything about the environment. But then in practice, of course, we do not know all about the environment. In any random environment, we cannot know everything about the environment. So that in this example, this is model-free RL, model-free RL, so that we do not know anything about the environment. So it's more practice, right? It's more practical. And we do not know probability in advance. We do not know anything in advance. Just so that our goal is getting Q function, optimal Q function from this one, model-free RL. This example is like getting optimal Q function from model-free RL. So You understand? So previous one, we directly calculated Q function with model base RL, but here our goal is the same, getting optimal Q function from model free RL, assuming we do not know everything, we know nothing about the environment. It's more practice. It's more practical, sorry. And so that here we can introduce the algorithm 1, 2, or 3, anything you prefer. We've learned 3 algorithms to get optimal Q functions, right? So here we only choose the algorithm 1, which is the brute force one. So let's say initial state is state 3. This is initial state 3. And then from state 3, and then going right, then it gives us 0 reward, right? So that we have 0 here. And then from state 4, there can be, there are 3 take actions that are available. And then what makes the the Q function the most? But unfortunately, we know nothing about the environment, so that we just perfectly rely on our Q table. And according to Q table, from state 4, all the Q functions are just 0, right? So that it becomes just 0. This becomes just 0. So that this number is just 0. We cannot update this one. So we just have the same 0. And then we visited state 4, right? State 4. We are now state 4. And let's calculate the Q function with the pair of state 4 and going up. How about this one? Then we have a reward, right? State 4 and going up, then we have reward 3. So that we have reward here is 3. And then from state 5, according to, for the among possible available actions that we can take, what is the optimal action that can maximize Q by the function? But unfortunately, all the numbers are 0, right? 0, 0, 0, 0. So regardless of action that you take, it always gives us 0. So that 3 plus 0, it gives us 3, right? And then we update the 0 to 3, right? We can keep repeat this. This is the, we can keep repeat this. And over here. And then let's get back to state 3 and going right. Let's revisit this one. Then state 3 and going right, it gives us 0. Still 0, right? Still 0. So that we have 0. And then from state 4, what is the action that can maximize the Q function? 0, 0, 3, 0. We have 3, right? So that we can choose going up as the optimal action. So that we have, this one is no longer 0. It has 3, right? So that 0.9 times 3 gives us 2.7. So that we update this 0 to 2.7. We can repeat this. Is it okay? I hope this is answer to questions of some student that asked me before. And then the assignment is about deep Q learning. So let me explain the assignment. Did we study the replay? 우리 이거 했나요? 안 했나요? Okay, then let's cover the deep Q learning, and then let me introduce the assignment. So, okay. So, I guess I introduced this one. So now we will implement a system for deep Q learning, but the problem is that we do not know the target. So, when training some neural network, we need target. So this is the output of network. We have neural network, which takes state and action and output Q value. That is the output with parameterized with theta. But we should know why. Which is the target of the reinforcement learning. But the problem is that we do not know Q value in advance for all possible combination of state and action. Of course, if we can pre-compute this kind of Q function in advance, that is good. But the motivation of deep Q learning is that it is too expensive to pre-compute this kind of Q table, so that we introduce a deep Q network to approximate this table, so that we do not know target ground truth Q function in advance. So instead of using pre-computed ground truth Q function, Q values, we get ground truth from this Bellman equation. R is from state SNA. So we have state SNA here, right? State SNA and gamma. So it's like almost same as Bellman equation, but the difference is that this Q is also from your network. So target is also from your network, and then we use theta from previous iteration. I could be, it might be Q minus 1 or Q minus I minus 10, I minus 1000. It depends on your design choice, but important thing is that we make some fixed iteration for making ground truths, and then we just use outputs from such network from previous iteration as the target. That is the philosophy of this kind of deep Q learning. So there are two things. Target is also from network's output. Target is detached because we do not want ground truth to be affected, so that we detach. So this one is detach. So my gradient is not backpropagate to the y. Gradient is only backpropagate to the current output. And then we use neural network with the previous iteration. So that is how we get ground truth Q function when training this kind of deep Q network. So we use, as I introduced, we use previous iterations output for the target, and that gives us definitely, it looks like very fragile. How about in early training stage with garbage values from random initialized Q function networks? So the training strategy of this kind of DQ network is that we use network's output to supervise the output. It's like it does not make sense at first glance. It could make so to make the network better, the ground truth should be good, but the ground truth is from incomplete network's output. So how can we guarantee that the convergence would be good? How can we guarantee such kind of optimization? So to achieve good optimization, people invented three systems, three stuff. The first one is that true reward as an anchor. As I said, we have R from state SNA, which is from predefined reward function, right? So that, true reward R is not from your network, it's just from our predefined reward function. So that it might be free from some garbage values from random initialized neural network. The actual environment reward provides, this is actual environment reward, it's like a R. It is not from network, it is just the actual environment reward, provides a ground truth signal, gradually correcting the inaccurate max Q prime estimates. That is the first thing, and the second one is high initial exploration. Epsilon is close to 1. So that epsilon close to 1 means we always take random action instead of exploiting what we've learned so far. It's like it's almost close to algorithm 1, right? The agent mostly ignores the untrained networks and takes random action to discover true reward. So instead of exploiting what we've learned so far at the early stage of the training, because in early stage of training we learn almost nothing, right? So instead of exploiting what we learned so far at the beginning of the training, we just let network explore the environment, so that you always take random action and then get some true reward from actual environment. And replay buffer warm-up, network updates are delayed until the memory collects enough diverse transitions using pure random actions. That is the replay buffer warm-up, which will be covered in next slide. And let's first see the examples of this kind of DQ network. Today's assignment is about card pool, but there can be many things like an Atari game. Atari game is like this kind of very some arcadic video games with simple graphics. So they try to maximize the score. The objective is complete the game with highest score. And state might be raw pixel input. We have some systems such as convolutional network that can process image and getting some useful features, right? So that we can just simply pass this kind of screenshot of each frame instead of passing metadata of the game. Raw pixel inputs of the game state could be state, which could be, so as I said, the deep network takes state and action as an input and outputs Q function. So state action, this becomes input of network. Another input is action, game control, such as left, right, up, down. We can, so these are four, so we can make a binary. We can make a one-hot vector. So this one could be, for example, 1 0 0 0 could be left, 1 0 1 0 1 0 1 0 0 could be right, 0 0 1 0 means up, and 0 0 0 1 could be down. So we can pass this kind of one-hot vector as an action encoding and then pass to the DQ network as an action input. And reward is score. We have score, right? We have score. Increase, decrease at each time step. As I said, so we can pass this kind of raw pixel of the maybe last 4 frames as an input that we can use any neural network actually, convolutional network or anything that is suitable for image processing. And single feed forward pass to compute Q value for all actions from the current state, right? And then we process this image, and then we have some FC layer, and then we have FC layers to produce Q value function for all actions. So last FC layer has 4D output if action 4 corresponding to, so you can design, it depends on your choice how you design Q network, but one possible design is, as I said, passing S and A as an input and outputs Q value function. That is one possible design. But actually the number of action is already predefined and constant, so that actually we do not need to pass the action to network. We can just let network predict Q value function for all possible actions, right? That is also possible. It depends on your network design. So this is like a second option. Instead of passing action as an input of the network, we can pass only state as an input of the network, and then outputs Q value function for all possible action. That is also a possible network design choice. So instead of passing action as an input, it only pass state as an action. And last FC layer, it tries to it's almost similar to the 4-class regression, right? 4-class regression. So because we only have 4 possible actions. Last FC layer has 4D output if 4 actions corresponding to STA1, STA2, STA3, STA4, right? So in last time I mentioned that this deep Q network or Q learning, such kind of stuff is only applicable to discrete action space, right? So here's the reason. So that we need Q values for all possible action, and then in continuous space, we cannot get actions for all possible state because the number of action is infinite, right? But for discrete action space, we can use deep Q network because the number of action is, it is not infinite. We have some predefined number of actions so that we can design network like this one. It tries to produce any Q value function for all possible actions. And the reason why we need this kind of experience replay that I introduced in previous slide is there can be many ways to train this kind of deep network, but the most naive way might be just let network play the game from every beginning of the game. So learning from batches of consecutive sample is probability. So I mean, at the first game, the video game might be consist of several stages. And at the first of the beginning, the neural network outputs almost the garbage values. So the network always fail at the first beginning of the network training. If network always play the same part of the video game, then it will converge in local minima. So that is about this one. Learning from batches of consecutive sample is probability. To obtain states, the agent must play through the environment, which produces sequence of highly similar temporally correlated states, right? The samples are correlated, sample inputs is always correlated, then it is inefficient learning, because the network always sees almost the similar things, but that it is not trained on some scenario, some episode with different states, totally different states. It always trained on very similar states. So current Q network parameter determines next training samples. Maximizing action is to move left. Training samples will be dominated by sample from left-hand side. Can lead to bad feedback loop. So what it means is that the training set, I mean, in one sentence, training set might be too simplified, too similar. It could be lack of diversity. If we just let network train play the video game, then the consecutive frames in the temporal space looks almost the same. So that we need to make training set more diverse. And that is the reason why we need this kind of experience replay. Address these problems using experience replay. Continually update the replay memory table of transition ST, AT, RT, ST plus 1 as game episodes are played. Train Q network on random mini-batch. Here, random mini-batch is important one. Random mini-batches of transitions from the replay memory instead of consecutive samples. So the game might be consist of several stages, like this is frame 1, 2, 3, 4, 5, 6, 7, 8, 9. This one. Frame index is just the 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm almost the same. There's no big difference between this mini-batch and this mini-batch. So the philosophy of experience replay is that we need to make training set more diverse, and then we pick random mini-batch of transition from replay memory. Let's see the algorithm description. So we initialize random replay memory and Q network. Here we have initialized replay memory, capacity N, and initialization value Q with random weights. It's just initialization. And play M episode, full games. We initialize state, starting game screen pixel at the beginning of each episode. And for each time step T of the game, with small probability, select the random action, otherwise select greedy action from current policy. That is, we know, right? This one is epsilon greed. Epsilon greedy. Algorithm 2 or 3. And take action, observe the reward RT, next state. So far, there is no special thing about the experience replay, but then here we have store transition. That is the experience replay. So we play the game. From current state, we perform some action, random or greedy action, anything we choose, we perform action, and we have updated state, and then we store this kind of transition from state to the next state. We store this kind of transition in memory D, which store replay memory. And experience replay. Sample a random mini-batch of transition from replay memory and perform gradient descent step. So far, this is exploration, explore. And this one, from sampled mini-batch, randomly sampled mini-batch, we update network, right? So that is difference. We let network explore the environment, and then we store transition in replay memory D, and then after that, for each iteration, we sample random mini-batch of transition from D, right? D might be full of stored transitions. right? While playing video games. And then we randomly sample mini batch from transition from memory D, and then update network with this one. And there can be a couple of ways to update network. Like if we introduce learning rate, then there can be a soft buffer to preserve current Q value function. If there is no running rate, then we can just overwrite the what we've learned so far. This is about algorithm 2 and algorithm 3. It's also different, but here experience memory, the philosophy of experience memory is that sample a random mini batch of transition from replay memory and perform a gradient descent step, right? The random is the important thing. Instead of always using the same similar looking state transition, we store this kind of transition while playing game and then randomly sample from the memory D. That is the experience memory. In this way, we can make training set more diverse, right? You can visit this YouTube link to see how our agent is getting better with this kind of experience replay. Okay? Any question?